Okay, let's get started. And again, if more of you can turn on your cameras, then I'll have a slightly better idea of what's going on in the class. Great. So let's get started here. And so we were talking about binary relations and uh, some properties of binary relations and how to use them for counting the number of elements. Okay, so let's refresh ourselves on uh, what these properties are, right? So uh, we, in particular, we want to talk about So we were talking about these three properties: injective, surjective, and bijective. So bijective is simply defined as the combination of the other two. So we only have to understand, surjective and injective, right? Surjective basically says that uh, every point on the right has at least one arrow coming in, right? So it says this greater than or equal to one arrow in property. So injective says kind of the opposite. It says that there is at most one arrow coming into every point. Okay, so let's keep that in mind, and then let's move on to understanding what these things mean, right? So A surjects B means that there exists some surjective function, right? So it doesn't have to be specified, but there exists some function that goes from A to B. Okay, so let's try to understand, visualize what this means. Okay, so and notice that we are being specific here that it is a function, right? So whereas surjective was simply defined as a property of relations. Okay, here when we say A surjects B, then we expect this to be a function. Okay, so let's try to understand what this means, right? So once again, this is A and that is B. And we are saying that there is a surjective function. So let's say what this means. So this means that if there are, okay, if there are some number of points, then there is a greater than or equal to one arrow coming in to each point on the right. Okay, so if we say maybe there could be multiple arrows coming into the same point, but there is at least okay. So there could be multiple arrows coming into some points like this, but there is at least one point coming into each of these, at least one arrow coming into each of these points. Okay, and then we are saying that it is a function. Okay, which means that, right? Remember what function means. Function means that there is at most one arrow going out, right? So you cannot, if you have, if you add this arrow, right, then this point has two arrows coming out of it. So it's no longer a function. So let's see if I can erase this selectively. Okay. So, so this means that the number of points on the left, right? The number of points on the left should somehow be greater than the number of points on the right, right? Because there is at least one arrow coming into the points on the right, which means that every point on the right is covered, right? And because two things can come into the same point from the left, right? Which means that if you go from right to left, there are going to be more points, but not less, right? So it could be the same number of points too, but certainly there is not, fewer points, because every arrow, right? Every tip of the arrow has a base, and we have already said at the base you cannot have more than, uh, uh, you cannot have a point having more than one arrow coming out, right? So if you just go back from each of these, then what it means is that you will reach a unique point on this side, because no point on this side can have two arrows coming out, right? So which means that if you start from each of these points, you can find at least one other point on the left, right, to pair up the point on the right. So every point on the right can be paired up with a unique point on the left, right? That's what A surjects B means, right? And this is why we can understand that whenever we find this type of relationship, that A should have at least as many elements as B, right? Because we are pairing elements from B with A, and we find that at least one element, one unique element from A can be paired with every element from B. Okay, so that's the meaning of A surjects B. Okay, so let's try to understand what A injects B. Okay, so once again, surjects always mean, think onto. Okay, that means every point on the right is covered. Okay, so that's the meaning of surjects. Now, injects, let's try to draw the picture of A injects B and then try to understand again what it means. Okay. Okay, so injects, if you look at the definition, it says that there is 0 or 1 arrow coming into every point on the right. Okay, so which means that, let's say, once again, we draw a few points. Okay, so maybe this arrow, this point has 1 arrow coming in, this one has nothing coming in, this one has 1 coming in, and this one has 1 coming in, maybe that. Okay, and now we are also saying that it is, so this is what it means to be injective, and then we want it to be a total function, right? Which means that, again, function means at most 1 arrow out. Total function means every point has an arrow coming out. Okay, so which means that, okay, so we have points here, and since this arrow going out of that point reaches at most 1 element, right? So and we have arrows coming out of every one of these points on the set A. which means that for every element in set A, we can pair it with some element in set B, right? So we have, say, 1, 2, 3, 4, and A, B, C, D, and maybe an E and F, right? So we can see that every element in A is paired with some element in B, but some elements in B may not be paired. Okay, this means that you have at least as many elements in B as there are elements in A, right? So this one, the first one, we argued that the size of A is greater than or equal to size of B. And just now what we are arguing is that B has at least as many elements as A, which is right, saying that A is less than or equal to B. And so let's just be clear. Instead of saying this, let's just say if A surge B and A inj B, right? So A surjects B and A injects B. If the two are satisfied, then obviously that means both of these conditions hold, which means that the sizes of the sets have to be equal, right? So remember what this is saying. A surjects B and A injects B means that from here you can see that every point here on B has to be covered, and because it's a function, every point on A is going to be covered too. So for a bijection, you have the property. Let's try to write this down, right? So a bijection right? So a bijection is a pairing of elements between A and B, right? So what we are doing here is we are taking one element from A and pairing it with one element in B. Now, and you're making sure that such that all elements have unique pairs, right? So there is essentially, you're making a matching, right? So matching each element in A with element in B, and we can say complete to say that every element is paired, right? So you can see that when you can arrange for this kind of matching, then you must have the exact same number of elements in both sets. Okay, so any questions so far? Some of this should once the way we visualize it, it all will seem, terribly obvious. And you might wonder, why are we bothering to say all these things? And the reason will become clearer a little bit later when we start talking about infinite sets. Because while our intuition works quite well when it comes to counting the number of elements in a finite set, when it comes to infinite sets, our intuition fails us. And so we need some, mathematical principles on the basis of which we can count the number of elements in infinite sets.
Professor,
Yeah.
could you say that a bijection is a one-to-one function?
Correct. It's a one-to-one function, but also it should cover everything on the right. Okay. So if you're familiar with the terminology of one-to-one and onto, right? So then it is a total one-to-one onto function, right? So that's when we say A bijects B, means there exists a one-to-one onto function that, from A to B, that's total.
Okay, thank you.
Okay, good. So yeah, again, don't get concerned if it all seems obvious, but I'm going on and on about something that's obvious. It's really for two reasons. One is that I want the terms surjective and injective are not particularly illuminating, right? I don't find them to have meaning that's immediately creates a mental picture of what it is. So for that reason, I want to walk you through these pictures again so that the visualization sets in. And the second reason, as I said, is that when it comes to infinite sets, we are not very good at counting them, so we need formalism to help us. So, but we are not ready to talk about infinite sets yet. So let's first use these three properties or three relations to count something that we know, which is the size of a power set. Okay, so let's start all over here. We started this in the end of the last lecture, and then I got cut off. Okay, so suppose we want to count the size of a power set. Okay, so I gave you a somewhat convincing but not entirely complete argument. So let's make that more complete. So once again, there are just too few of people who have turned on the camera. I would like to see like 30 people. Right now there are 9 people that have turned on the camera. Can you please go ahead and show your faces so I can, again, otherwise what will happen is that I'll be talking to these 9 people and the rest of the class is more likely to get left out. And I really don't want that. And in the last few lectures, we have been going through material that's not particularly complicated. I just wanted you to, so the goal of the lectures have been to get you more familiar with notations and definitions that we'll be needing to master. But you're going to find that very quickly this week, you're going to be, you can be lost very quickly if you are not, making sure that I'm paying attention to you, right? Because, so please turn on your camera so that way I have a better idea of who is here. Okay, so let's start by taking a set with 4 elements. Okay, So to count, so what we are asking is how many subsets of, let's say, let's call this A, right? So we're asking how many subsets are there. So here is a way to use bijections to count them, right? So what we're going to do is we are going to define, because there are 4 elements, so we are going to define a bijection from A to four-digit binary numbers, right? So 4-digit because there are 4 elements, okay? So the way this is going to be defined is, let's consider some subset X, okay? So for a subset X, we are going to map that a set X to binary number Y such that, okay, such that the ith bit of Y is set, right? Maybe I should, let's just, it's a 1 if and only if I is in X, okay? So let me give you an example. So if I have a subset 1, 3, okay? So I'm going to have, I'm going to construct a binary number Y, okay? And let's call this Y0, Y1, Y2, Y3, right? So there are 4-bit positions because it's a 4-digit binary number. So I'm going to ask, okay, so maybe let me call this Y1, Y2, Y3, Y4, okay? So just makes it a little bit easier to, so let's Y1, Y2, right? So because 1 is in the set, so I'm going to make Y1 to be 1. 3 is in this set, so I'm going to make Y3 to be 1, okay? And since I say it's a 1 if and only if that particular element is there, I'm just going to make, that means that the rest of the elements should be 0, right? So you can see that there is, given any subset of A, I have a unique binary number defined here, right? Similarly, if I have a binary number defined here, such as 1, 1, 0, 0, what would be the corresponding set?
Be 3 and 4.
So, right, so because that means Y3 and Y4 are set, therefore it should be 3 and 4, right? So given the binary number like this, I can immediately say, hey, this corresponds to this set, or given a set, I can correspondingly pick out the binary number. And this is unique, right? Because once I say this, these are the elements, then there is exactly one binary string or one binary number that corresponds to the set. Okay, so given the set, I can uniquely pick the binary number, and given the binary number, I can uniquely pick the set. Okay, so this is the meaning of bijection, right? So because remember, bijection says that I have a one-to-one pairing and everybody is covered, right? So therefore, I can take any set here, right? So what does the number 0 correspond to? The number 0 corresponds to what subset? Okay, I don't know how to pronounce your name. Maybe you can tell me how to pronounce your name, so I don't feel there's only one hand up. So let's.
Owen.
Yeah, go ahead.
0 would be the empty set.
So it should be the empty set because all digits are 0, which means that none of the numbers are in that set, right? None of 1, 2, 3, 4 are in the set. So 0 corresponds to the empty set. So given a set, we can uniquely find a binary number, and given a binary number, we can uniquely find a set, okay? And for every binary number with 4 digits, there is a corresponding set, and vice versa. So we have all the requirements for the kind of one-to-one matching, complete matching that we want, that characterizes a bijection. So we have a bijection, which means that the number of elements, right, the number of such subsets is equal to the number of 4-digit binary numbers, which is, of course, 2 to the power right, which is 2 to the power 4, right? The number of 4-digit binary numbers is 2 to the power 4. So once again, this may not be terribly new, because this is roughly the argument we made the other day to say the number of the size of power set of A is equal to 2 to the power of the size of A, right? So this is what we said the other day. And of course, all of this argument, which we made for a set of size 4, applies to set of arbitrary sizes. So we can say that in general, if a set A has n elements, then the power set will have 2 to the power n elements. Okay, so any questions so far? Okay, so we have how many of you have looked at the recordings and or had trouble accessing the lecture recordings and slides? Anybody who has had trouble? Anybody who has not had trouble? Can you lift your hand? How many of you have accessed the slides and especially the talk, the recording? Okay, so that's still only about less than half of the class. I would expect that by now all of you should have tried to access it. If you have any trouble, that means you need to tell me, right? And otherwise you'll find one fine morning the exam is in a couple of days, and you have a question and it's not you don't know how to get that answered, right? So you really need to make sure that you are able to access all of this material. Okay, so how many of you have looked at the next homework? don't be shy. Just lift your hand so that it's again, just to help me, right? And you can virtually lift your hand, which is probably what is easiest for me to see, because those of you who are not on my screen, I will have a little bit of a harder time. Okay, again, the last homework, there were maybe a couple of problems that it wasn't obvious it wasn't clear how to approach them for some of you. And then, but I think in this case, you may not have that much trouble with the individual questions, but there are a lot more of them. So if you don't get started early, then you'll find that the deadline is upon you, and you are only halfway through. So I encourage you, I urge you to take a look today and start working on the assignment, because again, you are allowed to work in groups, and the groups can be as large as you want, right? So we do that so that you can learn from each other, right? And but at the same time, when coordination is required, then you need more time. So you really need to get started on this homework as quickly as possible so that you will get it done, right? Okay, so let's go on to the more interesting topic of how do you count infinite sets. Okay, so we already said that for finite sets, these properties hold, right? If A surjects B, then A has at least as many elements as B. If A injects B, then B has at least as many elements as A. And if the A bijects B, that means you have the same number of elements in both sets. Okay. So now let's look at how to count infinite sets. So there are many things that we don't quite understand about infinite sets, but hopefully when we go back to this picture, right, showing surjection, right? What we are saying is that every element on the right is paired with at least one element on the left, right? So even if there are an infinite number of elements here, this way of thinking about counting the elements seems to make sense, right? Because what we are saying is that, hey, I don't know how many elements are here in the set B, but I can say that for every element in B, there is a corresponding element in A. Therefore, A must intuitively have, at least as many elements as B and possibly more, right? So this kind of reasoning where we are pairing off elements, right, seems like it should work even if we have an infinite number of elements, okay? And you can think about this more and convince yourself that this kind of reasoning seems to be applicable in the case of infinite sets as well. So once again, if there is a matching between elements of A and elements of B, and every element is paired, then again, it seems like that's really how we understand two sets having exactly the same number of elements. So we can apply that to infinite sets as well, okay? So that's what we are going to do, okay? Now, but there are a few unintuitive things about the size of infinite sets, okay? So let's take an example, right? So let us say that okay, so let's say that let's consider a mapping from n to n, okay, where right? So we can try to visualize this. So we can say 1, 2, 3, 4, 5, 6, and so on. And 1, 2, 3. Right? And well, we can start 0. So 0 maps to 0. 1 maps to 1. 2 maps to 4. And 4 maps to 16, right? Now, let's call this A, and let's call this B, okay? In fact, they're both N. The point that I'm trying to say is that you clearly have one arrow coming out of every element on the left, right? But a lot of elements on the right don't have arrows coming in, right? So you can see that there is one, because it's going from x to x square, right? So anything that's not a perfect square, that number is not going to have an arrow coming in on the right, okay? So these are the same sets. So every number, I'm sorry, let's see where we are. Right, so every number, every natural number has an arrow going out, but on the right, only a small fraction, small subset of the numbers on the right seem to have an arrow coming in, right? So this seems strange, right? Because we think, hey, these are the same sets. They have the same number of elements. Yet on the left, I have an arrow coming out of every element, but on the right, I don't have an arrow coming into every element. Okay? So what that means is that this is the function that I show here is strictly an injection, right? Because again, there is at most one arrow coming into each point on the right, right? Some of the points don't even have any arrow coming in. It's a total function because, you know, it's x squared, right? So it's a total function. So it satisfies the conditions of A injects B, okay? And typically when A injects B and there are elements in B that are not covered, right? Then our intuition tells us that you know, A has more elements than B. But in this case, we know because they are the same set, they must have the same number of elements. Yet we are able to construct these types of injections which leave out the vast majority of the elements, okay? So that's your first example of you know, how infinite sets behave in a strange way, okay? So the other thing to notice there is that there can be a bijection between two sets, right? Obviously, there's a bijection between you know, n and n, which simply maps the number to itself, right? If I draw an arrow from 0 to 0, 1 to 1, 2 to 2, 3 to 3, and so on, that's a bijection, right? So there clearly exists a bijection from n to n, but I can also construct this kind of an injection where lots of elements are left out. And if I flip A and B, right? So if I take, you know, if I take A and I flip it around, then I will have a surjective function, right? Because if I flip this, then if I flip each of the arrows going from B to A, so that all the arrows go from B to A, then there will be arrows coming into every point in A, right? And there will be, therefore it'll become surjective, right? So I can have a surjective mapping which leaves out again a lot of elements over here, right? So I can construct a bijection, but that doesn't mean that I cannot construct other types of mapping, right? So this is again a property of infinite sets that you would not find in finite sets. And the reason why it seems unintuitive that you could find this kind of a bijection while leaving out that you can find one mapping that's a bijection and a different mapping which covers all elements on one set but not all elements on the other set, right? That seems unintuitive simply because our intuition is only good for finite sets, right? Because that's what we deal with. That's what we have an intuitive understanding of. Anything that's unintuitive, then anything that's infinite, we don't have the intuition, and therefore we will find that these strange things happen. Any questions? No? Okay. So that says something unintuitive about the size of infinite sets. You can construct several other examples. So for instance, if you think about a function f from n to n, where f of x equal to 2x, well, once again, on the right, all the even numbers will be covered. All the odd numbers will not have any arrows coming in, right? And on the left, of course, there's an arrow coming out of every number, right? So that's another very simple example of unintuitive behavior, okay? So that leads us to asking this question of what is an infinite set, okay? We, of course, have some idea of what it is, but here is a way to think about it. And in fact, the way in which infinity is actually defined, right? So it says that a set is infinite if and only if the addition of one more element doesn't increase the number of elements in it, okay? So which we sort of, you would have informally said things like infinity plus 1 equals infinity, infinity plus infinity equals infinity, and so on. And all of this we will sort of explain in a certain way. So there is a hand raised. Is that for a question? If you have a question, again, you unmute yourself and ask the question. So that way, I don't miss you. So anybody who has a hand raised, if you have a question, just unmute yourself and ask a question. Okay, so let me just, I will lower your hand. Okay, so this way, maybe you didn't know that your hand was up. Okay, so how do we do this? Okay, so we will get back to how we so for a finite set, right? So if you add an element to A, so you have A union B, right? So this B, right? If you add a new element to a set, in a finite set, you will strictly have more elements, right? So that's why there is no bijection from A to A union B, right? Because if there is a bijection, that means they have the same number of elements, okay? But if you add a new element to a finite set, obviously there's a new element there. So obviously there's, you're going to have more elements, okay? But for infinite sets, okay, this is not true. So in fact, we have this definition that a set is infinite if and only if there is a bijection from A to A union B. Okay. So let's take an example, right? So to show that for infinite sets, you can do this, right? Let us take n to be our A, right? Let's set A equal to n, okay? And let's add the element -1 to n, okay? So let's call this B equals -1 union n, right? So we have an example of A union B and A, right? So A is n and A union B is B, okay? So now we can define this mapping, which let's define the mapping F, right? From B to A, right? And can you give me a mapping that's going to be a bijection from B to A? One of you can lift your hands. Yeah, Jonathan? Go ahead. You are muted.
The absolute value of the elements in B.
So if you take the absolute value, then it won't be a bijection because it'll map both -1 and 1 to 1, right? So remember, bijection means it has to be one element has to be paired uniquely with another element, and also every element has to be covered. Again, the things that you want to think about are matching, right? Matched pairs and everybody is paired, right? So you want to go from B to A in such a way that everybody is matched. Anybody else wants to try? Greg?
F of x equals x minus 1.
So, okay. So this will map. So if we write down our B, so that's -1, 0, 1, 2, 3, 4, 5, dot, dot, dot. And here is, 0, 1, 2, 3, 4, 5, 6, 7, dot, dot, dot. Then -1 will map to 0, 0 will map to 1, 1 will map to 2, 2 will map to 3, 3 will map to 4, right? And you can see that everything on the left is mapped to something on the right, right? And it is because +1, well, obviously it's a function, so it's going to map to exactly one element on the right. So this f of x equal to x plus 1 defines a pairing, right? That's a match, and it's also complete because everything on the left is covered and everything on the right is also covered, right? So we have defined a bijection, f of x equal to x plus 1, thereby creating a bijection between A and A, right? So we have created this bijection between A and A union B. And so this at least matches the definition, right? We know that the set of natural numbers is infinite. And so we are able to satisfy this requirement that you can construct a bijection from the set to the set union another element, okay? So this is sort of, and the converse also kind of seems, fairly intuitive, right? So if the addition of an element really doesn't make a difference to the number of elements, well, that means it can't be finite, right? So then it has to be infinite. If this is possible, then it has to be infinite, okay? So, among infinite sets, there are, it's not that there is one infinity, there are many infinities. So we are going to start off by with the infinity that corresponds to the number of natural numbers, okay? And then we'll show that there are sets which have strictly more elements than the number of natural numbers. But right now, let's start with by studying the set of natural numbers and what infinity means there, okay? So the particular notion we're going to use is countably infinite, okay? Which means that, so the definition of countable is that there is a way to enumerate, right? So the other term for countable is enumerable, right? So you can enumerate these elements in some order, right? So let's call it C0, C1, C2, okay? So the important property of this enumeration is that every element in the set will eventually appear, right? You can't say, oh, if you go on this list infinitely, then you will see the element. So that then it's not enumerable. Enumerable means that any element you pick, right, will appear after a finite number of places, okay? So which is sort of interesting and kind of shows you that natural numbers is kind of like defines this boundary between finite and infinite. Because with natural numbers, if you give me any number, right, of course I can count up to that number provided you give me enough time to live. But of course there are infinitely many natural numbers, but you cannot really give me a number that I cannot produce in this list if I keep listing 0, 1, and so on. Okay. So let's see what happened here. Okay. So so countable or enumerable means that you can list them in some order such that every element is going to be there somewhere in this list, okay? And if you go through enough of these, enough but finite number of these, then you will be able to find any one item in the set that you're looking for, right? We're not saying that every item in the set will be found after looking through a finite number, right? That's not true, because obviously if there are infinite number of elements, you can't get to all the elements after sequencing through only a finite number of them. But what we are saying is that if you pick any one element, okay, now that one element can be found after, if looking through the sequence through a finite number of elements in the sequence, you will find your number. Okay, so that's the definition of countably infinite or enumerable, right? So a countable set can also be finite, which is kind of not interesting because we obviously know that if you have a finite number of elements, you can list them in some order, right? So that's not the interesting part. The interesting part is that there can be some infinite sets such that you can list them in a certain order where any element you're looking for is going to appear there in that order after a finite number of other elements, okay? So try to, some of the things that we talk about is going to, can be difficult to wrap your head around for some time. And that's part of what we are trying to get you to do, try to sort of make you understand new concepts that are quite different from what you might have seen in the past. and hopefully that helps you sort of your mind grow in a sense, right? So that's really what some of these concepts are designed to do. Okay. So when we say that this can be listed in some order, right? So it's a way of saying that there is a surjection from N to A. Once again, you know, that may seem like a strange way of saying it, but basically what we are saying is that if you have the set C0, C1, C2, C3, C4, then we have this set N, then 0 can map to C0, 1 can map to C1, 2 can map to C2, 3 can map to C3, and 4 can map to C4, and so on, okay? And therefore, every element on the right is going to be covered, and there is going to be, you know, at least one arrow coming into each of these on the right. So this is a surjection from left to right. So what we are saying is that putting these subscripts on these elements and listing them is yeah, an intuitive way of pairing you know, the elements of N with the elements of this set. Okay, so we state that formally by saying that, hey, you know, there is a surjection from N to A, but saying that it can be listed in this way is more intuitive, and that's what we will you know, rely on in order to understand infinite sets a bit more. Any questions? You can ask questions that are, even if they are not particularly well formed, because the concepts are not very clear anyway.
So would an example be like you would consider the natural numbers to be countable because you can tell which position each element is in, but the real numbers aren't countable because you can't, like, for example, tell the position of like a repeating decimal, for example?
That's correct, but the reasoning about why real numbers are not countably infinite is quite involved, and we are going to get to that. But the intuitive reasoning that you have kind of doesn't work, because what do you think about the set of rational numbers? Is it countable, or do you think you can list them in some order? I mean, obviously, you know, if you have not heard this question before, and if you don't know the answer already, and you can create the answer right now, then you'll be a genius, right? So this is not a question that we know answers ahead of time. When somebody tells us, hey, this is why it is so, then we can hopefully understand, you know, that's the best we can do for some of these concepts. Okay, so so what do you think about rational numbers?
Countable.
Okay, so that happens to be true, and we will once again in a few minutes we'll see why you know, rational numbers are countable, and maybe we won't get to it today, but we'll also show that real numbers, you know, they can't be enumerated in any order such that you will be able to see the elements that you're looking for. Okay, so so again, countably infinite means it's countable and infinite, and there could be the term countable means that it can be either finite or countably infinite. Okay, so let's start with something very simple, right? So can we show that the set of integers, right, which includes both negative and positive whole numbers, can we show that Z is countable? Okay, can you think of a way to list the elements in Z such that every element will appear eventually in that list? Someone can, Brian.
Yeah, so you could start with the positive number and then go to the negative number. So like 1, -1, 2, -2.
Right, so the key is to alternate, right? So right? So if you list it this way, then clearly every integer is going to eventually appear in this list, right? On the other hand, if we say, hey, I will list all the positive numbers, and then later on, I will list all the negative numbers, right? Then there are an infinite number of elements out there. So in this enumeration, you will not get to any negative number after a finite, going through a finite number of elements, right? So this is not an enumeration that shows that Z is countable, but this one shows that there is a way to list integers such that every integer will show up. So many times, the common strategy for proving a set is countable is to identify an enumeration order. Okay, very often the strategy will involve this kind of mixing, right? So I'm not going to list elements of the same kind. Somehow I'm going to mix them around so that elements of every kind is going to have a chance to appear in this enumeration, and therefore all of those elements will eventually appear. So so we can also use another strategy which is based on closure properties of countable sets, right? So if A and B are countable, A union B is countable, A intersection B is countable, and A cross B is countable. Okay, so let's take A union B, right? So can you prove that if A and B are countable, A union B is also countable? Okay, which means that you have to show, so A is countable, so A can be listed as A0, A1, A2, right? So all elements of A can be listed this way, and all elements of B can be listed the same way, right? So now you need to find a way to list the elements of A union B such that every element of A union B will eventually appear in this list. So what is the way to do it? This should not be that difficult, so I should see more hands going up. Ron.
You could list A0, then B0.
Can you speak up a little bit? Let me also increase my volume. Maybe that's the problem that I have. Give me a second. Yeah, please go ahead.
Okay, so you could list A0, then B0, then A1, then B1, and alternate between them.
Right. So once again, this kind of mixing from the two streams, right? So you can think of it as two infinite streams, and I'm mixing them. And once I mix them, then everybody in both lists will eventually appear, right? So what about I'm sorry, let's see. This thing keeps. So by mixing the elements this way, we can do this. So A intersection B should be somehow obvious. right? So it's very clear that A intersection B has fewer elements than either A or B, right? So it's not surprising that A intersection B will be countable. But what about A cross B? Okay, so if we take this example, then, okay. So we have, things like A0, B0, A0, B1, right? And then A1, B0, A1, B1. Right? So the most obvious way of enumerating is this way, right? So you take A0, pair it with every element of B, then take A1, so that's how you obtain the first row here. So then you take A1, pair it with every one over there, and you get the second row. You take A2, pair it with every B, and you get the third row, and so on, right? So one way to go through this is, okay, I go row major, right? So I finish one row and then go to the next row. Then it's clear that I don't have the right enumeration, right? So what's going to happen if I just go row by row? Can you tell me what's the problem if I say I'm going to finish one row and then go to the next row?
Does one row ever end, or?
I'm sorry? Yeah, go ahead.
Wouldn't the row be infinite if there are, if you're pairing infinite elements, and then you'll never get to the next row?
Right. So this is a case where the rows are infinite because I already using these dots, I indicated that this is infinite, right? So the set B is infinite. So if you go row wise, I will never complete, right? So I'll never get to the second row, right? So no element in the second row will ever be listed if I say I will get to the second row after the first row. And if I go column wise, what's going to happen?
Same issue.
So you have the same issue, right? So is there a way to avoid these problems? Is there some way to enumerate such a way that you don't get into this difficulty? Is there some way of enumerating these elements such that you will get to every element eventually? Anybody? Frederick.
Oh, yeah.
I think this is similar to the proof I saw for the countability of rational numbers, but you can start at the top left element and then go down one and traverse top to the upper right diagonal, and then move over one and traverse the diagonal again.
So the easiest way to visualize this, understand this, is using a picture, and that's what Frederick was trying to say. So you start here, you go down one, and then you go diagonal, right? And then you can go to 2, and then you go diagonal on 2, right? And then you go to 3, then you go diagonal on 3, right? So if you go this way, so basically this is like starting, okay, so there is this infinite matrix you can think of, right? So each row is infinite, each column is infinite, but what you're doing is you're somehow going kind of diagonally, right? Basically what you're doing is that as you go take the next step diagonally, then you are going to list all the elements over there, right? So, and at every finite distance, right, this diagonal is going to be finite, right? So if you go 3 steps, then the diagonal at that point has something like, if you go 3 steps, then how many elements does it have? 4 elements, right? So it's 4 elements. So so you start, you have 1 element here, then you're going to have 2 elements, 3 elements, 4 elements, 5 elements, and so on. So as you keep going farther and farther from the top left, right, you still are only seeing a finite number of elements. And so you will, you can keep making progress. You're not going to get stuck anywhere because there is nothing infinite that you're encountering, right? So this traversal will eventually get to every one of these diagonals, right? Eventually, and therefore every point will eventually be visited, right? Okay, so now that we understand how A cross B can be listed, we can quickly answer why the set of rational numbers is countable, right? Because the rational number is something that can be expressed as a pair or of the form P comma Q, right? So let's take where P and Q right are integers, right? So let's take Z cross Z, Z cross Z, and we can define a bijection to Q, right? Because we say P comma Q in Z cross Z is going to be mapped to P divided by Q in. So there is a bijection between Z cross Z and Q. Therefore, Q must have the exact same elements as Z cross Z. And we have already said Z is countable. Therefore, Z cross Z is countable. And therefore, Q should be countable. Okay. And if this bijection thing is not convincing for you, you can, of course, take this strategy of enumerating, and you can enumerate these P comma Q pairs using this strategy over here, right? So that's what it will give you. So,
sorry, could I ask why it would be a bijection rather than a surjection?
because, okay, so so we are being a little bit careless here because when we say P by Q, multiple P by Qs correspond to the same rational number. And if I have sort of ignored that and pretended that every P slash P divided by Q is in fact a distinct rational number, okay? So that's why it's a bijection.
Okay, thank you.
Okay, so you don't have to do that. Of course, you can be more careful and say that P by Q, where P and Q have no common divisors. But the point is that you can easily see that if I allow repetitions, then I'm going to have more elements, and therefore, if I say P divided by Q with repetitions is countable, then of course P divided by Q without repetitions is still going to be countable. Okay, so you can also prove that rational complex numbers where you have a real and complex part, both of which are rational. Okay, so we can show that this set of complex rational numbers is also countable because this is nothing but Q cross Q, right? So because P, it's again a pair where P and Q are each rational numbers. So it's basically the set Q cross Q. And so okay, so Q cross Q, and so you can say that, well, Q is countable, therefore Q cross Q is countable, and so on. Okay. Now, so let's come back to this later on. Let's very quickly try to give an example of a case where there is a set that is actually uncountable, right? Because so far, everything we have tried seems to be countable, right? So is there an example of something that's uncountable? So saying that something is uncountable is difficult, because it's one thing to create an order for listing where we can then say everything is going to appear in that list, okay? To say that there exists no such order is much harder, right? Because how are we going to prove that such an order doesn't exist? And so for a very long time, people had no idea that such a thing could even be proved. So, so it took a real leap to be able to prove that some sets are uncountable. And here is an example, right? So uncountability of infinite strings over 0, 1, okay? And the idea here is to suppose that somebody can, in fact, enumerate it and then tell them that they missed some element, okay? Because there is going to be an element in this list. I'm going to be able to give you an element that will never appear in this list, okay? And the idea is actually, again, once the proof is constructed, it is quite easy to understand. So let's say that somebody can list these infinite strings over 0, 1 in such a way that every string will appear eventually, okay? So my proof is going to consist of a string that will never appear in this list. And the way I'm going to pick this is I'm going to pick the first position of this infinite string so that it differs with the first position of the first string, right? So because it differs in the first position with the first string, it's definitely not the first string, okay? So similarly, I'm going to pick the second position to be different from the second string, third position to be different from third string, and so on, okay? So which means that no matter how many elements you go through, okay, if you've gone through I rows, then I'm going to give you the ith position where it's different from the ith string, and therefore by construction, this string is different from the first string in the first position, second string in the second position, third string in the third position, fourth string in the fourth position, fifth string in the fifth position, and so on. So it's going to be different from every string that you're going to list, okay? So in a sense, it's a counterexample. It's a witness that says, I'm different from everybody else in this list, okay? So this type of proof technique is called diagonalization. And in fact, it's the kind of proof that is used to prove that there are undecidable truths in computer science. And in fact, you might have heard of the so-called halting problem, which basically asks whether a certain program will terminate when given a certain input. And some very smart people showed that this problem is undecidable, okay? And the way they proved that it is undecidable is basically using this technique. So let's wrap up here, and then we'll continue on Thursday. Okay, so once again, we want to start your recitation fairly soon, right, at 4:30, so that you can be done with the recitation and have some free time afterwards. Okay, so make sure that you be there on time. Don't be late. Your Solar might say 4:45, it might say something else, but the time we start is actually 4:30. Okay, so thank you. I'll see you on Thursday.